Welcome back to the long game. We are on a mission to demystify the science that shapes our lives and to unpack how great ideas built here in Scotland become real world medicines, devices, and new companies at the cutting edge of life sciences. I'm Ross Kagan, Regis Professor of Precision Medicine at University of Glasgow. Hey, Sandy.
Hi, Ross, and I'm Sandy Weir, Tech Innovation Leader and Strategic Program Manager, joining from Edinburgh.
Well, on the long game, we explore the collision of cells, code, and capital in the Scottish life sciences sector. As always, Sandy, lovely to see you. All good with you?
Yeah. It's been a busy week, Ross. But there's always something exciting happening for us to discuss in the world of Scottish life sciences. I must admit, I really look forward to this moment each week now, and it's great for us to be focusing and sharing another little bit of our worldview. So, shall we get started on this one? What do you think?
Absolutely. And like you, I always look forward to these as well. We were just chatting how we're getting a little obsessive over some of these topics and so on. But I am learning buckets, and I hope everybody is enjoying it as much as we have. And in fact, we're actually starting something different today, and it's going to be the tip of a larger iceberg, as everybody will learn. So, in addition to talking about specific biotech topics and interviews, we also wanted to expand this now that we're beginning to build a community. And today, we're going to start a series that explores some of the historic breakthroughs from Scotland that impact our current day biotech scene. So, we'll discuss a Scottish breakthrough that completely revolutionized global medicine. And today, I'm super excited, Sandy, because it happens to be the foundational technology for your current career.
Yeah, that's right. So that's so true. Yeah, I guess I wanted to share a little bit about our intentions for this part of the pod, and Ross, we both love to understand the historical milestones that have kind of shaped the life sciences landscape that we know, and we feel there's a lot that can be learned, and there's a lot that can be reapplied by looking again at some of the challenges that people have faced in the past, recapturing, I guess, the essence of the approach, combining information and experience around the timing of the technology, the opportunity, needs, the business conditions at that time, and then how these breakthroughs have really what's made them so successful. And so today we've decided to start by looking at magnetic resonance imaging, or MRI, or MR, as we tend to just abbreviate it to. And today, MR scanners, they're one of the most vital pieces of equipment in any modern hospital. But the very first clinically used full body MR system wasn't built in Silicon Valley. It wasn't built in Boston. It was actually built right here in Scotland by a dedicated team at the University of Aberdeen back in the 70s.
Yeah, I have to admit, in researching this, I was just kind of blown away. It's really an amazing story of physics, actually some clinical bravery, which we'll get to, and with the lead researcher often referred to as his team of half mad scientists. So this sounds like fun. Let's get into it.
Yeah, well, Ross, I guess it might be useful for our listeners to understand a little bit about the background. And I guess if we start off by thinking about, radiology imaging, if we think about X-rays, X-rays are fantastic. Everyone will be familiar with having gone and maybe they've had a fracture or something in the past. But X-rays have two big limitations. I guess the first is that they use ionizing radiation, and we have to be careful on how much exposure we give to patients. And of course, frequent x rays, cumulative dose, that can be really hazardous. And then I guess X-rays are really good for revealing the bone, the skeleton, and some level of soft tissue, but they're not really good at that. They're not very good at revealing any sort of detail in soft tissue, and particularly sort of soft wet tissue. So good at bones, not so good at other parts in general. Now, X-rays are 2D, and if we consider CTs, that's the sort of bigger cousin of the X-ray. These are computed tomography scans. These are also based on the same technology as X-ray, so they use ionizing radiation, but they produce these 3D cross-sectional slices of bone, vessel, soft tissue, much, much more detail. They allow us to visualize organs. They allow us to guide biopsies and assess trauma, look for different pathologies such as tumors. And of course, the key thing is these provide much, much more detail than a 2D X-ray. However, if you're really looking for true detailed views of tissue in the human body, such as the sort of tumor that's hidden inside an organ, really important to visualize, an X-ray won't do that. A CT won't provide the fine detail, and this is where magnetic resonance images or MRIs, this is where they become incredibly useful. So MR is the magnetic fields. These are not ionizing radiation, which is a very important distinction. And they can deliver these highly detailed images of soft tissue. They're excellent when we need to visualize these tissues, such as muscles, ligaments, complex tumors, tumor environment, and detailed brain imaging. So there's a little bit of a kind of starter for us.
Actually, this is really helpful because I am constantly confused by these various technologies. So the X-ray, the CT, the MR, which I remember to say MR. So I got it. So they have advantages and disadvantages. So before we really jump into the history of MR and why we're so excited about it, do me a favor. Can you summarize each of these for us just to sort of complete the picture about where they stand when somebody walks in the door?
Yeah. Let me try and do that. So X-rays, I guess these are where most people have encountered, most people's experience. They'll understand that these are very fast. They take typically just a few seconds, certainly less than a minute to capture once the patient's in position. They're very low cost in comparison to the other technologies. So say, something like $50,000, although there are more costly high spec clinical specific functions, particularly around cardiology. But these are X-rays ideal, as I said, for detecting things like broken bones. CTs are fast. They take several minutes to perform, but the systems are much more costly. So say somewhere between 100K, 300K, although again, there are some very high spec systems that are available that are more costly even than that. But these are ideal for imaging internal organs, looking for bleeding, musculoskeletal imaging, and in low dose applications, they're excellent utility for screening, for example, as well. So things like early detection of lung tumors, we see that as an increasingly important use case. But because both CT and X-ray are based on ionizing radiation, we have to be extremely careful, as I mentioned, to avoid overexposure to X-rays. So, for example, got to be very careful around X-ray CT during pregnancy. And then we've got MR, which is what we're talking about today. And typically these take much longer. So they're often around 30 to 60 minutes to capture an MR. These are much more costly equipments, say several $100,000 or even into the sort of 2, 3 million, depending on the specification of the system. But these MRs, these have the unique ability to provide that very high level detailed images of soft tissue. So looking at things like ligament tears, spinal cord injuries, brain tumors, this is where they really sort of come into their own. And importantly, as I've mentioned now, and I'm going to keep mentioning it so people understand, MR does not use ionizing radiation, so they're much safer in that respect. However, we've got to be careful with people that have got things like metal implants, so things like pacemakers, for example, because these are really important considerations. So, they're not completely safe for everyone. We have to be mindful of the patient history and the other interventions that have taken place in the past. So each has its place, Ross.
Got it. So basically, yeah. So it's obviously safer because it's all about stepping into a magnetic field. And I know some of the crazy stories about people who have accidentally stepped into those fields. But I really appreciate this. So that's a great summary. And so now we can step back and now we can talk about the incredible history of how MR imaging actually evolved. So, in the middle of the last century, the medical community needed a way to look inside the body, as you said, and to safely see soft tissue. And I actually think MR is going to, as it gets better and better, it's going to kind of take over a lot of that imaging field because it's safer and you can get more detail in principle. Anyway, so we need to talk about Professor John Mallard. So in 1965, he moves to Aberdeen to take up the newly created chair of medical physics. And actually, pretty amazing guy. So I've read a fair bit about him now. He was deaf from childhood, didn't seem to slow him down in any way. He basically was top of his class as he went through his education. He became really a crack physicist and somehow became interested in basically the physics of hospitals and hospital testing and so on, which I guess in retrospect is obviously a field, but I had just not thought much about it. And he had a particular interest in magnetic properties of electrons and how we could use those in tissue samples. And actually, he was the first person to notice the difference between normal tissues and tumors and even published this in Nature, which, for those who aren't familiar, is one of the top journals in our field. Somehow, nobody really particularly noticed this paper. Nobody really thought it was particularly useful, except for this dude, John Mallard.
Yeah, that's right, Ross. It is an incredible story. And what we understand is, of course, that he started assembling this especially brilliant team to crack this problem and to really overcome the issues that around making this technology useful. And this team included a physicist named Jim Hutchinson, who began putting together the equipment to measure the magnetic resonance signals from the hydrogen atoms in the body as they're excited. And actually, it was the Aberdeen MRI project that literally became a marriage of physicists and biologists when he ended up actually marrying the team's biology member, Meg Foster. And that's what I call cross-functional team integration, Ross.
Oh, okay. So, yeah, very nice, Sandy. So the Aberdeen, they obviously had worked out the theory, this being driven by John Mallard. As you say, he put together this incredible team, but still, they had to make it an actual physical reality. So Hutchison brought in and teamed up with this guy, Bill Edelstein,
Edelstein, yeah.
an American physicist who had actually moved to Aberdeen. He had originally done a fellowship at University of Glasgow, and he had actually originally come to University of Glasgow to research gravitational waves. Remember those? Those have been hot recently. It was probably wise of him. He did switch to the Aberdeen MR team because he realized that resonance was much more likely to succeed in his lifetime, and in retrospect, that was probably a good move.
Yeah, there's always a connection back to the University of Glasgow, isn't there, Ross?
Maybe,
So it's good for us to
possibly,
get that one in.
possibly.
Yeah, that's right. And Edelstein, he's a great example of like yourself, Ross, Scotland's ability to attract and retain global talent. And he ended up staying because he fell in love with the country in a big way, but apparently also, alas, from Dumfries. So again, there was that really strong connection with the country, and together that team then with Hutchinson, Edelstein, they designed and built what became the Mark One, and that was the world's first clinically used whole body MR scanner.
Yeah. And I definitely get a pattern of coming here to marry. Um, but actually, the hardware was just part of the battle. Actually, the real genius, as I'm sure you know better than most, it's actually the software and the physics algorithm they invented to run it. Called this thing spin warp imaging technique. And apparently, they called it spin warp because the proton spin columns they measured resembled the warp threads of woven cloth.
Yeah, and that algorithm really was the game changer, as you quite rightly say, Ross. It was the very first method to produce a full, clear image of the tissue of the whole body using MR. And then the ultimate test came on the 28th of April, 1980. Ross, that's nearly 46 years ago to the day as we're sitting doing this recording of the pod this week. And they used the Mark One for the first ever diagnostic MR full body scan at the Aberdeen Royal Infirmary.
Yeah. Actually, this day must have been absolutely amazing. I'm sure because they clearly understood the impact of what they were doing, probably better than anybody. So the first patient was a terminally ill man from Fraserburgh who had cancer, and the scan successfully revealed very clear images of his cancerous growths. So unfortunately, it was too late to save his life. That's not the purpose of the MR. But he had volunteered as a guinea pig specifically to help save lives of others in the future. And I have to say, I'm always blown away by my own experiences with clinical trials, how people are willing to help people with their lives, for the future. You like to think that if you have something bad with you, that you can at least turn some of that into a positive. Certainly with this patient, who I would say obviously is somebody who deserves note as well. It is a key moment in medical history, and it really shows how these sacrifices of patients, how important they are for developing these new technologies. They obviously didn't know what to expect, right?
Yeah, exactly. And actually, we talk about the brilliance of the scientists, and
Mhm.
indeed they were brilliant in creating this technology. But that patient was so brave because I don't know if you've seen the images of that system. We all recognize an MR these days. It's those donut shaped systems that with the hole in the middle where the patient enters in and to allow them to be imaged. Well, the this early version, this was essentially still a prototype, although it was a clinically function prototype. So it took
Mhm.
a lot of guts, a lot of bravery for that individual to really put themselves forward as the first patient. So incredible bravery. Then I guess if we start to think about this from a commercial perspective, so sorry, Ross, I always have to break it round to the sort
I
of
know. That's why
commercial
we're here,
side,
my
the
friend.
business side. I guess what happened next is also pretty amazing. So from that point, 1,000 patients were scanned on that Mark One before it was finally replaced with the next version in 1983. But that spin warp technique that Hutchinson and Edelstein invented didn't just stay in Scotland. That became the foundation standard that was used in all commercial MR systems worldwide.
Because we are willing to share. Of note, and slightly annoyingly, um, in 2003, the Nobel Prize for Medicine for the development of the MRI of MR was awarded to the American Paul Lauterbur and the British physicist Sir Peter Mansfield. But it's interesting. It was really clearly the Aberdeen team's spin warp technique that actually made the technology useful for the whole body. And I was thinking about this. If they had given that prize today, would they have been more willing to recognize the people who actually turned this into, practical use? I think that's more commonly with these Nobels today than it was in those days. I don't know what you think.
Yeah, yeah. I mean, I like to think the same thing, Ross. I like to think they would be more equitable in the recognition, but really, the whole development really underscores the economic value and of the translation and the opportunity to translate. You can discover the underlying physics, but it really takes the people to figure out how to engineer that application, how to make that spin warp algorithm into something that's suitable for a clinical setting. Those are the ones that really created the multi billion industry that it's become. And today, companies like GE, Siemens Healthineers, Philips Healthcare, and my own company, Canon Medical Systems, we've really built on that exact legacy.
Sure. And even the insight to something as straightforward as, hey, look, you can distinguish a tumor from normal tissue. I think that actually took that technology and just said, oh, this actually would be useful. So, anyway, one of the reasons that we're starting with this MRI, which here in Scotland I think is really taken with some pride, and we haven't talked about x rays, but actually that is also something of a Scottish story. And maybe we'll get to that at some point. But that really has sort of echoed forward to today. We see this in Scotland. You and I see this.
Yeah.
We know, and I know we interacted as part of our activities in Living Lab with ICE, the Imaging Center of Excellence in Glasgow. They have an ultra high 7 Tesla MRI scanner. I assume you've seen this.
Yes. Yeah.
I
Yeah.
certainly have it. The images from it are wild. The detail you can see, for example, in the brain is just mind blowing. We're going to have to come up with some images and maybe post those. So maybe I can get some to put it in there. Really, that's the first 7 Tesla MRI scanner in the UK. Um, and so basically, the boundaries that John Millard and his team established 40 years ago in Aberdeen, now we're just seeing the echo that moves forward. When these guys break the ground, then we all sort of build on top of that. And actually, I'll just give a shout out again, learned through the Living Lab, to MR Coil Tech, founded by Shejan Gunamoni. Oh, I was pronouncing that right. Which is building bespoke RF coils to continue to improve the imaging on this already amazing Tesla MRI machine.
Yeah, we've got a lot of respect for MR Coil Tech and what they've achieved, and
Yeah.
actually it's interesting, Ross. I remember I was just kind of in the latter stages and about to leave the NHS in Glasgow when that 7 Tesla MR was being installed, and I think that was back in 2014, 2015, and I remember the excitement of that system being delivered, the first 7 Tesla in the UK, and the it was real kudos to Glasgow to have that as one of the defining systems in the ice building and the imaging center of excellence. It really was. It's a brilliant story. It's a great reminder of how much global medical infrastructure relies a bit on Scottish engineering, which is always nice to reflect on.
Hmm.
But I guess it's probably time to wrap up this part of the show now, Ross, and come to the bit that we look forward to every week, the final segment, a wee bit of joy. And Ross, please tell us what's brought you a wee bit of joy this week.
I was just thinking of the phrase that I always hear here in Scotland since I've been here, which is that we punch above our weight,
Yeah.
which I think I like. So my my joy this week is very simple. I hope you can see a little difference, which is I just got a much needed haircut. And inspired, and I'm sure you're thinking, all right, where is he going with this? So actually inspired by one of your previous Wee Bits of Joy where you did
Oh.
some digging back. I did some digging into haircuts and barbers, seeing if I could somehow link them to healthcare. So, let's do this. So it turns out in 1505, the Town Council of Edinburgh formally recognized the incorporation of surgeons and barbers. Let me say that again, surgeons and barbers.
Yeah.
That's right, Sandy. For over 2 centuries, that person cutting your hair was the same professional you would visit for bloodletting, treating battlefield wounds, having a tooth pulled, pretty much any surgery that you would have. In other words, in principle, in those days, I could get Andrew Biancan to fix my tumor and give me a low fade. In fact, surgeons and barbers didn't actually formally separate their trades till 1722. I don't know why I love this, but I really do. Just finishing this riff. So hair is something of a biological flight recorder. Because your hair grows so slowly, it retains long-term biochemical timeline. So it's
Yeah.
almost like the rings of a tree, if you will. And if we talk about mass spec on a single strand, because why wouldn't you? We can measure, for example, chronic stress by looking at trapped cortisol levels. We can track how my body's absorbed drugs. So you can do a drug test on me with my hair, as some people probably know. You can and detect exposure to environmental toxins, all this stuff over many months. And there's so much to learn from hair, but alas, it's all left on the barber's floor. Shout out to Gellin's barbershop. Oh, and I should probably mention, just to finish this, as a tip of the hat to our upcoming AI segments, there is an AI-driven automated set of hair clippers that gives you the perfect fade every time, at least from what I could see. So my question to you, Sandy, is this. Who would you trust more for your next haircut? A surgeon like Andrew or an unsupervised set of AI clippers?
Oh, that's a terrible dilemma. That's a terrible dilemma. If Andrew's listening, I'm sure Andrew doesn't want to cut my hair, but I'd be quite excited to see what a set of AI clippers could do.
Ooh, I don't know how Andrew's going to feel about that, but yeah, I'd probably
And
go
I,
the
I,
same.
I hadn't I hadn't prepped for this, and I didn't know what you were bringing to your wee bit of joy today, and that was a fabulous story, Ross. But it kind of reminds me, just an interesting fact. You've probably also noticed that outside barbers in the UK, they typically have a sort of red and white stripe pole, diagonal stripe pole. And that's because apparently back in the day, back in the 1500s, 1600s, the surgeon cum barber would also hang the bloody rags of the whatever operation he'd been doing outside on a pole outside
Ah,
the shop, and I
I
guess
love
that
it.
stuck as the icon on the high street for where your barber was.
I love it.
Yeah, but that's a great story. And yeah, sorry, Andrew, I'm going to go with the AI clippers.
Yep. Sorry, Andrew.
Yeah, well,
How about you, Sandy?
yeah, thanks, Ross. Yeah, so for me, a wee bit of joy this week was going to the theatre. And Helen and I, my wife and I, we went along to the Festival Theatre on Saturday in Edinburgh to see the High Life musical spectacular. Now, I know what you're thinking, Ross. What's this? The High Life? What is that? Well, it was a short-lived Scottish TV comedy back in the 90s with Alan Cumming. I'm sure you've heard of Alan Cumming. He's an
Yeah, yeah. I
international
love Alan
actor,
Cumming.
very
He's awesome.
famous actor,
Yeah,
and a Scottish comic actor called Forbes Mason, and they were a bit of a double act back in the 90s. And this time they brought that musical to stage as a musical comedy, a sort of pantomime, really, I guess. But the premise is that you follow a dysfunctional staff of a fictional boutique airline called Air Scotia. And the show was known for its kind of slapstick, camp style of humor. Fans of Alan Cumming that turned up to the theatre, they were not disappointed. It was an absolute riot. The reassembled cast were fantastic. The show was brilliant. It was a lot of fun, a lot of laughs. Um, I guess if you try and pick it apart at a more intellectual level, they were somehow fusing together the challenges of reconciling the past, kind of growing or trying to grow old with dignity, and something that spoke to me is the challenges of what we call sleeping with an elephant. Scotland's age-old battle of maintaining its identity and its belief systems whilst keeping these relevant while constantly being under pressure from our much larger southern neighbour. And I'll just leave it at that. I wouldn't name check. But anyway, you get it. So there's all that rolled into one. And
yeah.
I'm getting too deep, but it was great. It was really good fun. It was absolutely hilarious, and I thoroughly recommend it. It might be touring now, so I think the theatre companies, the Dundee Rep Theatre Company, which is also famous for producing talents like Brian Cox. You've probably heard of Brian Cox as well.
Yeah, of course.
Anyway, simply quite brilliant. If you get a chance, please go and see it, but go and see anything. Anything that's on the stage, I think, is always so much more vibrant and engaging. So yeah, go and see it if you can.
Yeah, something that at least my American friends will not know is what a panto is,
Oh,
because
yeah,
I'd
pantomime.
never heard of a panto until we came here. So someday we'll talk about that and what a panto is. It
Yeah,
sounds like this is
yes,
some version of that, which I have to say they're really a ton of fun. So that
yeah.
sounds amazing. It sounds like a lot of fun. Well, I think it's time for us to end this between the hair and the stage. So I wanted to end our first historical podcast on a quote from John Mallard, the star of today's podcast, who really had to fight the system to get his vision made. And the quote is, "Persevere in your endeavors to the end. Success or failure, ignore even those powerful people who say it won't work. And there'll always be plenty of those."
Yeah, that's powerful words. So keep that in mind. And until next time, folks, as Ross, you like to say, keep the heat. And yeah, the best of luck continuing to play the long game. Thanks very much
Enjoy
for
the
joining.
pantos, everybody. Ciao.
Bye.
Yeah, see the vision clear. We're here to run the long game. Blueprint set, no fear. Playing out the long game, the long game.